All right, thanks everybody for coming out. This is the last gasp before the party tonight, so I commend you all on your assiduousness in coming out in the late afternoon, and hope to be able to keep you awake for the next 45 minutes or so. Hello to the people behind the light there. All right, so my name's Tim Bray. I'm an engineer at AWS, and I did a lot of work on step functions and even have some code in there, so I have familial feelings about it. And to help us out, we got Patrick Brandt here down from Coca-Cola to talk about some of the things that they're doing with the technology. This is a 300-level session, and there will be code. I hope that's okay. A few organizational notes. I think we're pretty well going to use all of the time we have today, so let's not do questions from the stage. However, Patrick and I promised to go outside there and stand around and talk to anybody who wants to talk about step functions until our voices give out or you fall over or something. Is there going to be beer out there afterwards, or do you have to wait for the party for that? I don't know. Okay, so let's dive into this. So we released this product at this event last year. There's Werner standing on stage in last year's ugly t-shirt talking about step functions, and since then we've filled it in a bunch of regions around the world. That job is not finished yet. If step functions is not available in your favorite region, sorry, we're getting there. And integrated it with a whole bunch of the basic AWS infrastructure, just trying to be a better citizen of the AWS platform, the cloud formations and so on, of that type of stuff. But, and then just a couple of weeks ago, we announced support for in-place updating of state machines, and anybody who's worked for the product will appreciate that. Coming soon, actual version numbers. But at least we can update them in place, which is a step forward. But we are not here today to talk about what we've been doing with the product. We are here today to talk about what you've been doing with the product, because there have sure been a lot of applications. And we're going to dive into a few of those that we selected just because we thought they were interesting or instructive or just out and out crazy and might have lessons to offer those who are just starting to get into this subject. Now, I suspect there are some of you in the audience who have a question in your mind, which is, what is step functions anyhow? And unfortunately, I'm not going to spend a lot of time doing a deep dive on what this product is, but don't get up and leave, because that's okay. One of the important points I want to make about this product, it is a very, very simple service, even though it doesn't have simple in its name, and maybe there's a pattern in that. When I gave the talk on the service last year at this time, I had to really work hard to pull together 60 minutes of material, because there's just not that much stuff to talk about here. Fortunately, now that we've got people building stuff to talk about, we got more ammunition. So here are the basics. Step functions is all about orchestrating the units that go into making up modern microservice-based applications. What does that jargon really mean? Well, stick around and you'll find out. Now, step functions is 100% serverless itself, and we are, after all, on the serverless track here, but shh, it's okay for that other stuff too. Step functions is just fine with old school code that's running on an EC2 instance or an ECS container, or even, I perish the thought, on your own computer in your own data center, although why would you want to do that? But it makes sense to have it on the serverless track, and in fact, the content of today's talk is pretty well all serverless stuff, because there's a really, really strong affinity between step functions and Lambda. Lambdas represent small, discrete, lightweight, event-driven units of compute, and it's the most natural thing in the world to say, well, I want to run this Lambda and then that Lambda, or I want to run these 5 Lambdas in parallel, or I want to run this Lambda, and if it blows up, I want to retry as many as 5 or 6 times, and that's what step functions does. So step functions and Lambda really, really, really work well together. So I'm going to close with a claim, which is that if you're sitting out there and you haven't really looked at step functions yet, or only lightly, I'm going to claim that by the time we get finished with this, you will. You'll know what it's about. And that's because anybody who's ever written specifications or a textbook knows that your eager readers skip lightly over your beautiful walls of text and go straight to the examples. And that's what we're going to do. We're going to do like an hour of examples here. So let us dive in. We've started to see some patterns emerge, and the most obvious initial pattern is a lack of a pattern. The things for which step functions are being used is a truly all over the map thing, all kinds of applications, more different kinds of things than you can imagine. And I'm not really surprised at that. For an old guy like me, it's not surprising when you ship a general purpose technology and people use it in ways you don't anticipate, because that's how the world works. But it's kind of amusing to hear the young engineers on the Step Functions team looking at bug reports or feature requests and going, what the beep? I mean, give me a break. Why would a person want to do that? Well, what's going on is that there's a phrase that these young geeks have heard, but they have not actually internalized. So seriously, you know, when you ship something that's horizontal and general purpose, you should expect to be surprised, and you should absolutely, definitely not expect people to share your particular vision of what this thing is for and how it was meant to be used. Having said that, there are a couple of patterns that are worth mentioning. When I was standing here last year, I pointed out that whereas this is a large scalable elastic service that can do, you know, thousands of transitions per second, it would have a place in the world replacing shell scripts. And that prediction turned out, unlike many of my predictions, to be right, because I know that a lot of you are automating your stuff with shell scripts. Nasty, little, write-only, unreviewed, uncommitted, source code controlled shell scripts. And we would never do things like that, but you know, you shouldn't. And it actually turns out to be pretty straightforward to drop in a step function to replace one of those. And it also has the virtue, when you do that, you end up with all your logging in one place and a nice audit trail and better retries than Bash knows how to do, and so on and so forth. So that turned out to be true. And that actually, I remember I went and visited Major League Baseball last spring, shortly after the service launched. And they told us how they were setting up with step functions to do all sorts of upgrades and installations and migrations that had formerly been Bash scripts. And they were enthusiastic. They said, this is great, you know, we're going to be running hundreds of machines a week. And I was thinking, well, we actually built it to run millions of machines per hour, but still, that's okay. It's still a success story. And, you know, anybody's got to cheer over the grave of a Bash script. And actually, this turns out to be an okay way to get into modern serverless distributed application architecture, because after you've done some of these little automation things, you've developed enough skills and familiarity and chops to you know, go ahead and launch into another larger application. And that's what we've seen, specifically in the second half of 2017, larger and larger and more complex applications. And one example of a customer who did exactly that was Coca-Cola, who started out with a simple application to work around a problem and has been branching out. In fact, it was interesting enough that way back earlier in the year, Jeff Barr did a blog. I don't know why you put a picture of the other Jeff in, but it looks okay, about what Coca-Cola and Patrick here had been doing specifically. And then Coca-Cola has moved on and done some, you know, much more ambitious stuff. And fortunately for all of us, Patrick from Coke agreed to come down and talk about it. So let me bring up a really red and white slide, and Patrick, take it over.
Right. Thanks, Tim. Hi, everybody. I'm Patrick Brandt. I'm a IT director and solutions strategist for marketing operations and product development at Coca-Cola. And we're going to look at a couple of examples of how we use step functions to solve problems, big problems, in those two areas. I'm going to start with marketing, in particular, the vending pass program. So the vending pass is a digital card that lives in your mobile wallet, Android or iPhone. You can use it to earn and redeem free drinks at supported vending machines. You can also purchase free drinks for your friends and share them with them through the vending pass, which I recommend you doing if you want to have lots of friends. But as we were rolling this program out in 2016, we identified a pretty significant edge case that could have caused a lot of dissatisfaction with our consumers. Now, this is kind of a complicated scenario, so I thought the best way we could walk through it together is for me to tell you a story featuring our hero Isaac, his friend Alice, and Isaac's vending pass. So Isaac and Alice are out on the town, and Isaac has a free vend, man. He's totally stoked. He's going to get a free drink, and he's going to buy one for Alice. So he taps his phone to the payment device on the vending machine, which is that yellow box there. And then he's asked a question, or he was asked a question at the time. And the question was, do you want to use your vend now, or do you want to save it for later? But you'll notice that in the meantime, his vending pass is displaying 0 vends. He hasn't actually purchased a drink yet. So this is the root of the problem, right? This is where all the drama begins. And we're going to look at this in a little more detail a few slides in because it's important to understand what's happening here. Anyway, so Isaac says, since you asked, machine, I changed my mind. I've decided I'm going to pay with cash. He buys a drink for himself. He buys a drink for Alice. She's very happy about that. Later that day, Isaac notices that he has 0 VINs on his vending pass, even though he didn't purchase his drink with his free VIN. So now poor Isaac is very confused and he's frustrated and he doesn't trust us anymore. And we don't want that to happen. So what's going on here? In actuality, Isaac's balance in the back end and the database where we store vending information is correct. He has 1 free VIN. The problem is that that information has gotten out of sync with the user interface, which is the vending pass. So to understand the details about this, we have to wade into the weeds a little bit around how our payment system works. So when Isaac touches his phone to that payment device, that emits an event. It's called a card swipe event. When he selects a drink, pushes a button, and the drink falls out, that emits a second event. It's called a track payment event. It means that the payment's been authorized and the transaction is complete. So for reasons I won't get into, we'll call them legacy architectural debt, which is not uncommon in business. We can only subscribe to one of those 2 events. And because the program at the time was allowing consumers to keep a free VIN or use it at the point of sale, we had to subscribe to that first event, that card swipe event. So what would have happened is Isaac taps the payment device, it emits that card swipe event. We put a 60-second hold for the price of a VIN on his balance, and then we would have to have updated the vending pass UI right away. Excuse me. So if Isaac were to walk away or if he were to pay by a different means, that hold would expire and his balance would be made good. He'd have his VIN back. But again, legacy architecture, we don't have a way to subscribe to that event and update the pass. So what's the solution? It's really simple, actually. We just need to wait. We just need to wait for any latent holds to expire, and then we update the pass. So 60-second hold. At some point after 60 seconds, go and get Isaac's information, update the vending pass. So we implemented this as a step function, which is we implemented a very, very simple state machine. There are 2 states in our state machine. There's a 90-second wait state. Again, 60 minutes plus 30, the balance will be good. And then there's another task that invokes a Lambda function that goes back to the vending pass database, or the vending database, and updates his pass. So now the solution here, Isaac touches the vending pass, the payment device, and emits that card swipe event. We put a hold on his balance, and then we publish a message to an SNS topic that causes a step function to begin executing. It goes into a 90-second wait, then it wakes up, and it invokes a Lambda function that updates his balance on the vending pass UI, if necessary. So at no point now with this solution does the vending pass display a balance that is less than what Isaac actually has, which is important for making sure that Isaac remains happy and trusts us.
Well, now hold on a second here. So we shipped a fully managed, large-scale, durable, highly available AWS service that can do thousands of state transitions a second, and you used it to put in a 90-second delay.
Yes. Yes, we did. And it's fortunate, Tim, that Step Function can handle so many transactions, because keep in mind that every time a vending pass user touches that payment device, a step function execution is initiated. And this is user traffic, right? These are effectively unbounded. We could expect spiky loads, if they're campaigns or promotions. And then, obviously, we can expect growth over time.
So how would you have done it if you didn't have step functions?
The next easiest solution would have been to just use a Lambda, right? A single Lambda function. It's node. Those who know node know that you would write a set timeout, 90-second. That'd be your first line of code. And then after that, you'd have the function that actually, or the code that actually does the work. The problem with it, we didn't feel good about that, though, because that function that updates the vending pass balance actually it executes in less than a second. So the idea that we would burn 90 seconds of idle time and compute to do less than a second of work we felt like maybe we could do better. And so it turns out that with the pricing model of state machines versus compute time with Lambda and the state transition costs, et cetera, it is more cost effective for us to implement this using step functions. So AWS found that among their customers, this pattern of scheduling, or this need to schedule future work was so common that they created a task timer blueprint. And you can find this blueprint online on the AWS doc site if you need to do workloads similar to what we're doing or some other things that I think Tim will talk about later. This is a great place to get started. So thanks to Tim and the Step Functions team for putting that together for all of us. All right, moving on to our next example, and this is a big one, big one. The Food and Drug Administration here in the United States published new requirements for nutrition fact panels in 2016. There are some significant changes. You can see here, for example, calories are more visible, but additional information has been added, like added sugars. Also, more details are provided around certain nutrients that are contained within the food. So you can imagine that this is a really big deal for us. We sell over 100 different brands in the United States in over 800 different package configurations. So that's roughly 800 fact panels that need to be updated. It's also a big deal for our food service partners because they are required to display nutrition information on premise in the restaurant. They also sometimes need to publish it online. And so they need our nutrition information to comply with these guidelines. So we've been doing this for a while. The original fact panel was, it dates from the 90s. And we have existing infrastructure and personnel to, ensure that we're complying with the FDA guidelines. The team within Coca-Cola that is responsible for making sure we're compliant is called Scientific and Regulatory Affairs. And I'm going to refer to them as SRA for the rest of this presentation. And they work with a nutrition database. They do nutrition analysis on each one of our products, and then they store that analysis in the database, and they publish it, which sends it to a downstream system that our packaging and graphics team uses to actually print it out on labels and boxes and et cetera. So as you can see, foreshadowing on the slide, initially we had some problems with our legacy platform. When the SRA personnel, when the SRA staffer would publish data, that would cause a mashup of stored procedures and shell scripts and legacy ETL jobs to swing into action. And then about 18 hours later, data would show up downstream, and it was very often invalid or malformed. And so then that, of course, necessitates a round of communication between disparate teams so that it's additional hours. We've got to trace down the problem, we've got to fix it, and then just to verify that things are fixed correctly, you're looking at another 18 hours, okay? So 800 fact panels, 18 hours, best case. You can see how this might not work out for us. We needed a faster, better way. So the first architectural move we made was to lift all of the transformation processes and validation and business rules out of stored procedures and shell scripts and ETL jobs, and to put them into step functions. So now when our SRA personnel publish nutrition data, it simply emits raw data into the step function where the processing begins. Even better, if there's a problem in the data, if a validation issue is caught and detected, an email alert is sent to our SRA staff. They get immediate feedback if there's a problem. As soon as they click publish, if there's an issue, an email drops in their inbox. That means that all of that conversation between a bunch of people is completely obviated and unnecessary now. So provided that everything's working out, data shows up downstream, nice and clean, packaging team has nothing to worry about. This process takes 10 seconds. So we had 18 hours best case to get the job done, but very likely double that at least. And we've reduced that down to 10 seconds. So we're in a much, much better shape now to adhere to our very, very important regulatory guidelines. And then obviously as we produce more products in the future, we have less effort to comply with FDA rules. A really nice upshot though of adopting step functions, and this was pretty unexpected, I think, is that it facilitated communication between two very different groups of people. On the one hand, you have SRA, who are, unlike most people, experts in nutrition and FDA guidelines. And on the other hand, you have developers who, like a lot of people in this room, know how to code and deliver software. And so the visual medium of step functions was an exchange for ideas. And it began with Mary from SRA creating data flow diagrams and decision trees and whatever, and then sharing those with Perry, the developer, who would then implement them as a step function. Once that was done, those two shouldered up, and then they logged into the AWS console together, and then they watched in real time the state flow. They sent in known good data, they sent in known bad data, and they verified that everything worked as expected. A great advantage here is that through observing this, Mary could identify optimization. She could see where new validation and new transformations could be introduced that actually provided value to the overall business. And that could never have happened if we didn't have the ability to watch the state function, the step function operate in real time. So it's worth mentioning that Perry and Mary, great team. They are real people, just not these people. This is the entire architecture of the system, and we are going to step through this. No pun intended. One step at a time. Applause? No? Okay. So step one, changes to nutrition data are published. That sends a raw JSON payload, a request to an API gateway endpoint. That JSON is stored in Elasticache, key value pair. The key is published to an SNS topic. That then initiates the execution of a step function, which operates against that data that's stored in Elasticache. If an issue with the data is detected, an email is sent via SES to an SRA group. Provided everything's okay, the data flow forks. On the one hand, it goes up, it's stored in Aurora. That effectively publishes it through an API that's hosted in an API gateway in AWS Lambda. This is where our food service, This is where our food service partners can pick up our nutrition data. On the other hand, a message is published to another SNS topic that triggers the execution of another step function, which simply takes the valid data and then molds it into a format where it can be more easily ingested into Salesforce. This particular step function, the transform formula nutrition step function, is the hub of this entire architecture. So we're going to look at this one in a little more detail. Yes, you might notice one thing. It's huge. This is no two-state state machine like our prior example. There are actually 94 tasks in this state machine. So we're not going to look at all of those. I would like to focus, though, on this first set of parallel state machines. I kind of think of them as mini state machines that perform very specific units of work. So we have a mini state machine that validates that there's a canonical ID, another one that validates the serving size info, and another one that verifies that the data is good for fact panels that have display more than one serving size. Anyway, so each one of those smaller state machines results in a Boolean value. It's did it work or not, true or false. So those Boolean values are aggregated via a set of tasks further downstream. If everything's true, the state machine branch continues to do more work. In the case that invalid data was detected, so in this example, invalid serving size data was detected, that little state machine branch goes down it flows down a different branch that creates that error-specific email body, and then it has another task that sends that email out through SES. That fail state, that Boolean value, is detected, and then it causes the entire state machine to flow into a fail state, which ends the step function execution. So this has all worked very well for us. Like I said, we had this surprising win in how productive we could be by reducing the distance and the communication between our business and our development team. At the same time, allowing business and development to view the action of the state function in real time opened up a lot of possibilities in terms of enhancements and improvements that could be quickly implemented thanks to our ACE developer. One thing we're still working on, managing large state machines. 94 tasks can be unwieldy if not handled properly. We've started to migrate this work, or I think we actually have migrated the configuration into the serverless development framework. It has a plugin for step functions, and it just allows us to more cleanly define our tasks and bind the Lambda functions that those tasks are using in one place.
Oh, right. So we promised these people code.
Yeah, let's do that.
You can't sit down until we've done some code here. So this is from one of the branches at the top of your three-way fork parallel validation at the top. And I ran a script over this thing, and I noticed that in this thing there were 39 distinct Lambda functions.
Yeah.
So,
yeah.
Wow.
Yeah. So our development team took or adhered to the single responsibility principle of software design. And the outcome of that is that we have very granular, very atomic Lambda functions. So that means that they can be composed to perform a larger unit of work, like one of those 3 parallel state machines. Or a Lambda can be reused. And that happens frequently. Anytime we send an email, we are, in fact, invoking one Lambda. It just happens to be bound to different tasks.
I seem to think that's the way they taught us to do software in school, you know. By the way, we're going to be looking at a few state machines, and I light up the state names in purple in all of them, so that's what we can talk about. Easy way to find things on the screen. Another thing I found in there was, this was the exit of one of your parallel states, and way down at the bottom, there's this bit of code. What's going on with that output path there?
Sure. So again, this is a little bit more of the configuration for the smaller state machine that verified that there was a canonical ID. In any case, if you look at this, we have a choice state, and if things are true, we move down into this drink code valid task. So what we have to do is we have to end the state machine execution for that little state, right? And that's exactly what this succeed type task does. It does no work. It just ends the execution of the running state machine. At the same time, though, because we have 3 state machines running in parallel, little state machines running in parallel, and we want to aggregate the true or false value for each one, we have to pass out the result of the validation. And that's why we're using that output path.
So in fact, you're throwing away everything but the Boolean that
That's
came
right.
out of that.
And then we test that further downstream.
Interestingly, when we were designing the service, I didn't think the output path field was necessary, and I didn't want to put it in, and the team got together and shouted me down, and apparently they were right and I was wrong. So I ran another script over this, and came up with this, and I pulled out the state names, and so, wow, now that's what you call a state name. Eh?
Yeah, no, that's some, that's
so,
some, we won the longest state name award, people. If I parse this out, right, prepare notification cannot modify formula not in draft status error. Well, embedded in there is a business rule. We cannot modify formulas that are not in draft status. So you may not know what that means. I don't know what that means, but SRA knows what that means. And in fact, we do end up with some fairly verbose task names, but that is because we work directly with the business to define them. And that's very important when we talk about posterity. We're going to have to maintain this in the future. We'll probably have to enhance it in the future. And being able to capture the business domain and represent that in a way that our business can understand is critical, because it's going to save us a bunch of time in the future, obviously. So I will say that perhaps there's an opportunity in the future to make this a little more semantically fluid. And yeah, we can put white spaces in there. That's awesome. But at the same time, our goal of being able to communicate what this thing is doing to the business has been achieved.
Okay, well, there you go. So Coke started small, and they've gone big, I think we can all agree. That's an impressive piece of work, and I sure learned a few things looking at it, so thank you kindly, Patrick.
Yeah, you're welcome.
Oh, there you go. I want to take a very quick side trip. I noticed, so Patrick sent this thing down for me to look at, and it wouldn't fit on any of my screens, and I have some really big screens. So I found myself running little scripts over it. And I think there's a lesson in that. The fact that the states language is in JSON makes it extremely tractable to do that kind of thing. We were under some pressure to embed it in Python or make it more like a programming language, which had some advantages and was not an insane idea. But at the moment, I'm kind of glad that it's in JSON, so I can do some automated analysis. And in fact, after I looked at it, I confessed that I ran a script to find the longest state name, just so I could make that slide. So thanks, Patrick. So let's talk about some other kinds of state machines. So this one isn't terribly complex or deep, but this one came across my radar while I was looking at that 90-second delay problem that Coke had. And Husay have a bunch of marketing-related products, but their real special niche is working with media influencers, which is a very common marketing vector these days. And what they want to do is when a celebrity or an influencer posts, it's their job to figure out what the impact of was that and quantify it and measure it and do lots of analytics on it. And that turns out to be a very time-sensitive thing. And I think anybody who has a social media following knows the feeling. You come to work on Thursday, and some tweet you did on Tuesday got picked up by Hacker News, and your blog post now has 25,000 views. So these people need to understand that kind of flow of influence around the social media ecosystem. So Coke got a substantial business benefit from putting a single 90-second delay in there, and these guys took that to the max. So at one level, this is the simplest thing in the world. They use Lambda to run their analytics, fully stateless serverless application, and they have one parallel state with 11 wait states in it and launch the Lambda 11 times. In case you can't read the text on the screen, they wait for 1, 5, and 30 minutes, then 1, 2, 6, and 12 hours, and then 1, 2, 7, and 14 days, and then re-rest the analytics. And that is actually a capture from a live running execution, and you can see that the 1-minute thing has fired, but the rest of them, the 5-minute hasn't yet. It's still coming along. Well, you could achieve a similar effect, I guess, by having something running on a server that wakes up every minute and looks in a database to see if it's going to do anything, but most times it wouldn't, and you'd have to write the code to look in the database, and you'd have to write the database. And why would you do that when you can just do this? I said I'd show you the code, but I'm not going to show you the code for this one because it's boring. From their point of view, it isn't so much what this machine does, because you can describe that in a single sentence. It's how easy it was to set up. And if there's one thing point I'm trying to make in this presentation, it's that one. This is a simple service. It has no abstractions. It has no indirections. It has no new concepts. In our work life, it is the most common thing in the world to say, well, first we do this, then we do that. Or, we're going to do these things sometime over the next week. Or, we need to schedule a bunch of stuff to happen over the next quarter. And that's the exact kind of business process we're trying to model in a very direct, non-abstract way in here. So, having said that, it's not all as simple as this, as we've seen in the Coke example. Let's look at a couple of other applications. Both of these come from the world of video processing, but they do totally different things, and I think they illustrate different points. So first of all, let's look at the Thomson Reuters application. Now, it may be the case that we have one of the people who wrote this in the audience. Jeffrey, are you here? Oh, okay, there's Jeffrey. So Jeffrey, can you come out with us afterwards in case people want to talk about this and tell you how you did it all wrong? Okay. So Thomson Reuters is a news company, obviously, and are very widespread and influential. And if you follow the news at all, it's very unlikely you can get through a day without reading one of their stories or seeing one of their video clips. And they get a lot of video each day coming in, and they need to transcode it into 14 different formats to put it out on their many, many channels. And these vary wildly in their length, from a 3-second clip of a bomb going off to a 30-minute interview with a newsmaker. And they need to transcode it, and since this is news, they need to do it fast, no delays. They do it mostly with FFmpeg, and anybody who's worked with video is now nodding because, kind of more or less everything is done with FFmpeg. And that's a good piece of software, but it's single-threaded. So if you have, a 30-minute video clip, you can end up, and you want to transcode it, you can end up running FFmpeg for 30 minutes to accomplish that effect, which is entirely unsatisfactory if you're a news organization. So how did they solve this problem? Well, there you go. It turns out that if you look inside video, there are certain frames that are special, called keyframes. They come along every half second or so, and to oversimplify, the keyframe has the whole picture, and the next few frames are deltas against it. So, like it says there, they took it and split it apart, and, if you think about it, if these things are half second long, in a 10-minute video, that's 10 minutes, that's 600 seconds, so there's going to be 1,200 of these little fragments. So they'll split them up. Now they have one linear thing. They have to run through the whole thing to find the keyframes, but that's the only linear thing. Once you've done it, they can do the transcoding on all the pieces in parallel and put them back together. And in principle, they can take this, and not only in principle, in practice, they can take things down from many minutes to a small number of seconds. Now let's dive into this and look at it, because there's a bunch of interesting stuff happening in here. So I took that state machine and broke it up into two parts so we can fit it onto the slide. And you know, one of the big problems they fought with, and it wasn't the step functions part, it was the fact that FFmpeg wants to write into files. And you know, writing into files on the disk is not exactly a best practice in your serverless Lambda application, but you know, that's what FFmpeg wants to do. And in particular, when they've broken everything apart and they want to put it back together again, that's going to create a big honking video file. And so they did this following clever trick, which I just wanted to share with the geeks in the crowd for its cool factor. So they told FFmpeg to write it to a file, which is actually a named pipe that pipes into an AWS CLI command that dumps it out into an S3 bucket. Extra points for cleverness, I say. Now, if you actually, now they're still fighting with some problems because when they do the split, FFmpeg takes a file name template and wants to write a bunch of little files. And so, you know, no applications are problem-free, but their problems aren't step functions problems. Anyhow, the structure of the state machine is easy enough to understand. On the left hand, they run through and get ready to do the split, and I had to ask myself, why does it take 6 states to get ready and do the split? So we'll look inside and see. And then on the right, they loop around, wait for results, wait for results, wait for results until it's done. And I looked at this, and I could not see how on earth they were getting any parallelism, because there is no obvious parallelism in that state machine. So I asked Jeffrey, and here's what they did, is they get their 1,000 or 2,000 or 3,000 or whatever segments, and they blast them all into S3 as little object puts, and they wired up S3 to fire a Lambda for each one. So, you know, they're bypassing all this high-level machinery. And think about this, you know, 10 minutes, 1,200 segments, 1,200 Lambdas. They each take like 3 seconds to transcode a half second, and your work's all done. Then you just have to glue it back together. Once again, I got to say that's seriously clever. And then when they do the split, you can look at the step functions there. They just wait 3 seconds. Oh, and the reason this works is they know how many segments they got, right? So they just wait 3 seconds to see, oh, are all the output segments there? No. Wait 3 seconds, and that's how it works. Now let's dive in and actually look at some of the code here. So here are those 6 states at the front that they line up to actually do the split up. And when we designed the pass state, and you know, if you look at this, you can see there's a bunch of pass states here. Oh, I actually got it lit up in the slide. There we go. When we designed the pass state, we were thinking of that as perhaps mostly a debugging tool, but they're actually using it to insert fields in the data using the result path thing. They're setting the operation field to the value prepare split. So they're sort of setting opcodes in there. So I was scratching my head and looking at this and noticed that it's all the same Lambda function. All the Lambda functions that they're running through here are the same Lambda function. And so I asked Jeffrey, well, what's going on here? And he pointed out that basically all these things are just running FFmpeg. So they've got, you know, a bunch of little things that decide what the FFmpeg arguments are based on the opcode and fires off FFmpeg. And they said, well, you know, that was the simplest way to run it and manage their software, because all the stuff is there in one place that reads arguments and sets things up. So what's the best practice? Here, let's have a vote. Let's sort ourselves into baskets. There's going to be one basket for people who believe in having lots of small, single-purpose Lambda functions, and another basket who are sympathetic with combining it all. So who's in the many functions basket? Oh, yeah, I guess you would be, wouldn't you? Right. And who's in the shrink them down a little bit and have a manageable number? You see, we're still making up the best practices. We don't even know yet. You know, you know, it's a fun time to be doing this stuff. What else is interesting in here? Let's go on and look at their loop. Their loop is a little bit interesting. So the wait for result state is at the center of everything, and it's using a choice state to basically as a switch on the poll status top level field. Most times it goes, you know, to the looper, which waits 3 seconds and then runs the task to check to see if you're done, and then the very last step is the one that stitches them all together. So while this thing is waking up every 3 seconds, the 1,200 or so Lambda functions are thundering away, actually, you know, providing the business value by doing the transcoding, and then in the last state down there, they stitch everything together. Now, one of the things that's on our roadmap is to enable you to run a child workflow in a task state. And if we had that now, they could have probably lost 2 or 3 of the states in here and just run the child workflow and put a standard step function retry in there. But that'll be coming before too long. So what are the lessons of doing this? So basically, the maximum size of video that these guys can do this to depends on their Lambda limits, right? How many thousands of Lambda functions they can run in parallel. And it turns out that if you talk to the Lambda group, actually there was an announcement about that, wasn't there, today, that you can now increase the maximum number of Lambdas you can run in parallel just by asking for it. But I think that only goes up to a few thousand. And if you want to do like 120,000, which these guys might want to do, they can do that. You just have to ask them so that they're ready for it. Let me see. So even with, for half an hour, even with the time scanning through looking for keyframes, the whole thing is still going to be under 3 minutes in execution, which is a big win for them. And you could imagine doing this on EC2 or in ECS, but then you'd always be worried about scaling up for when you were doing it and scaling back out again. And what they've done is they've done the serverless thing and just handed the whole job over to Lambda and said, when there's work, do the work, and when there's not work, don't do the work and don't charge me. So this is an example of real, what I would call first-rate serverless thinking and taking the effort out of the scaling. Hold on a second. Did I miss something? Oops. Did I miss something here? Yeah, okay, I took all the takeaways. Okay, let's talk about another application. This is a startup called Frame.io, and they, I don't know how much you know about processing videos, but it's very, very workflow intensive. And you have teams of people doing various jobs, and if you haven't seen it, it's mind-boggling. The amount of work it takes to produce like a 30-second video segment is staggering and involves lots of people working together. So Frame is all about automating that and providing a good workbench. Now, they do a lot of video processing of one kind or another. And since they are somewhat less newsy and less constrained to get things done in seconds, they do things in a simpler way. And in fact, they want to do all their short video processing in Lambda. But if it's a long video, they'll send it off to a Docker container and let the Docker container grind away on it till it's done. And that works fine. So this deceptively simple problem of how to decide, how am I going to do this work, is what drove the start of this thing. So there's actually a lot to talk about in this simple thing. They had actually stitched a super ad hoc thing together based on SNS and a bunch of procedural code reading the SNS topic and so on, and it wasn't good. So what they did was they built this. And before we say anything else, I got to say, isn't that a great looking state machine? Isn't that pretty? Prettiest one I've seen. And so what they did was they used the state machine to pick which execution engine they were going to use. And you'll notice that there's a call out to CloudWatch Events here. And it's a super clever thing, and I'll come back to that later. But there's their state machine. So let us dive inside that state machine and look what's happening. So here's how they actually go about deciding whether they're going to go to ECS or Lambda. And this is super simple. They say they're going to go and use a Lambda if the asset size is less than 2 gig, or is that 20 gig? Anyhow, a lot of zeros there. And they're also going to do it if the duration is less than 10,000 milliseconds, which is to say 10 seconds. So that's simple to understand. It does make me wonder if so it says default, go and run the ECS encoder if it doesn't meet these conditions. Maybe we should have just named that else, because that's what they're just using it as an else. And in fact, that's how it's being used in all the state machines I see. So let's go and look at how they actually go and run the ECS. The one when they run the Lambda encoder, there's nothing to it. It's just a single task state in the state machine. There's nothing fancy about it at all. So here's how they go and they run their ECS decoder. And it's a straight enough task state, and they actually use a Lambda to kick off the ECS task, and that's easy enough to understand. But then I kept looking at this, and I was thinking, what are they doing? In English, they're retrying this thing every 5 seconds for an hour. So I talked to them and I said, what's going on here? And they said, well, here's what's going on, is they are using the ECS Run Tasks API to do this. And it turns out that if your cluster doesn't have anything available to run your container, it'll just say, no, sorry, I can't, see you later. But that's okay, because the way they've got this set up is that if it's running hot, Autoscaling will notice and crank up the cluster size a bit. And maybe another one will finish running. And eventually a slot will clear up and it'll work. And this kind of looks like using a hammer to hit a thumbtack, but it actually works just great for them. It's totally hands-off. It doesn't rely on anything very fancy, and eventually all their work gets done, and they're happy. So when they get finished with this, they go off to the last state, which over there on the bottom right, which they go off to a state named ECS task complete, which exists to wait until the ECS task has finished its work. Now, are there any Ruby programmers in the room here? Because if there are, dig the state name with a question mark at the end. That's very, very Ruby flavored, and I like that. I think that's so what kind of a state would you put an exclamation mark at the end of, I wonder? But in Ruby, if you have a function that is basically returns a Boolean, you always put a question mark in the name of it. So that's what they're doing here. Okay, so this choice here is a little bit on the complicated side. They've got this complicated AND condition, which basically says, if this thing blew up or I tried more than 3 times, well, we'll go and decide that we failed and give up for now. The real loop part is over here. That just jumps back to the code on the previous slide. And this is another customer who would benefit from being able to just, say, run a child workflow, because once again, they could just put some retries on that, and it would just go straight through. Now, there's one more interesting thing here, which is that both the succeed state and the fail state down here, they don't just exit the workflow, they go and fire CloudWatch Events. Now, for those of you who don't know what CloudWatch Events is a bus that has all your events on it for your AWS account. So all your API calls from CloudTrail, when EC2 instances start and stop, when auto-scaling scale up and scale down. There's events from like 14, 16 or something services in there now, and it's really easy to route them to Lambdas or to state machines or to other things. One of the things that's not that well known is that you can put your own events on the event bus with CloudWatch Events. And that's what they've done. They've actually put their own custom events on the event bus. And this is a lovely, lovely application. So the way it actually works, it's an event-driven architecture. It's powered by CloudWatch Events, and they've got multiple state machines. Each one sort of they think of as a microservice, and some of the microservices may have a couple of state machines. And when the video gets uploaded, that generates a CloudWatch event that fires the first state machine, and then it does its work. So it's a fairly intricate 3-level orchestration. The events floating through launch the state machines, and then the state machines in turn orchestrate the Lambdas and the ECS tasks to get this done, and it's all serverless. There's no fleet management code. There's no deployment code. There's just none of that stuff. It's like in that big slide Werner had in his keynote this morning, essentially all the code they wrote was business value code, the thing that they were actually doing the work that the management thinks it's paying for, not all the other stuff that we have to spend our time doing and would rather not. So this whole thing really smells like something like a real serverless application of the future here. Now, they had to do some extra work to accomplish this because they're running this same job through multiple state machines and Lambdas and ECS tasks. They had to keep track of it, so they put a correlation ID. Now, I'm wondering if they would have been able to have done that with X-Ray, once X-Ray is more widely supported across the services. But you know what? I think it's a pattern here. I think it's a pattern that we're going to start seeing a lot of people doing correlation IDs just to keep track of units of work as they flow through this kind of postmodern serverless framework. So what else worked well for them? They went with SAM, and SAM is working like a champ for them. They went back and forth between SAM and mirrorless. Mirrorless is great. I love it. In their case, they didn't really have any multi-cloud requirement at all. So with SAM, they could do it all in CloudFormation, more or less. And so that worked really well for them. The other thing they did that I thought was terribly clever is they're using Code Pipeline. And they've actually got Code Pipeline set up after they've built things and deployed. It fires off a CloudWatch Events to pretend that a video has come in. And that, in turn, sets off the whole cascade of step functions and Lambdas and ECSs and CloudWatch Events. And their CI/CD also posts a handler for the CloudWatch Events they expect to see coming out of the system assuming everything worked. So not only is their serverless application of the future easy to operate, it's easy to test too, in a nice hands-off way. For those of you who haven't looked at CloudWatch Events pattern matching, go have a look at it. It was a big win for these guys. It's a nice little feature. From their point of view, they are super happy. They have something that is totally hands-off, requires no administration, basically grows and shrinks to take care of itself, operates really, really fast. They're heading towards running 2,000 a minute or so, 2,000 or so videos a minute through this thing, and nothing's running hot. The costs are very, very reasonable to them. So I like this application. I want to do a case study or a paper or something on this application. It really feels like what the future is going to look like. I am getting run down here. Those are all the state machines I'm going to show you, but there are lots more of them out there. And there's the URL for them. You can write it down, or you can wait for this to go on YouTube and just capture it from there. Or you just go to the state machines console, and it's right there. So we have a lot more sample state machines out there. Go look at them. I recommend strongly that if you're going to build one of your own, go there first and look and make sure somebody hasn't already done it. But moving forward, I want to leave you with two messages. The first is, this is an easy service to use. No abstractions, no new concepts. Purely serverless, fully managed, really, really elastic. The barrier to entry is low. Go and find a bash script and kill it and drop one of these in, and you'll find out how easy it is. If you're putting together an application with this, the putting together is going to be the easy part. The problems, this isn't where your problems are going to be. They're going to be in the hard parts, where your own hard business problems are being solved. Now, the second thing is, I think all of us in the serverless space, we need to be honest and acknowledge that we're kind of just making this up as we go along. We don't have an accepted best practice Bible we can go look in. We don't even know what the conventional wisdom is. I mean, we got this room evenly split on how many Lambda functions you should have, right? That's the stage of history we're at right now. And this is the fun stage of history. This is when we're, figuring out the right way to do things. Should we have lots of functions or just a few? We've got lots of ways to do compute now. We've got bare metal, we've got instances with EC2, we've got containers and a whole bunch of flavors, and we've got functions. Which is the right one? Well, which is the best flavor of ice cream, right? It totally depends on what you're doing. So let's work this out together. Who's going to make the discoveries? Who's going to work out the best practices? Who's going to become conventionally wise and have the conventional wisdom? You are, not us, right? Bill Joy famously said, wherever you work, most of the smart people are somewhere else. And, that would be you. So right now is the time for us to sort of work together as a community and figure out what the best practices are, what the practical wisdom are. And the way you can do that is by sharing. So when you do something in this that is interesting and novel and perhaps instructive to others, they put it up on social media somewhere, and use that Step Functions hashtag. And what we're going to do is we'll promise to be watching that. We watch social media pretty carefully, and we'll filter that out, and we'll, if we see anything that's interesting, we'll probably ping you and ask if we can share that, if we can put it on the page, if you can come to reInvent next year and talk about it, because making it all up as you go along is kind of fun, but it's not really sustainable. We do need to work together to figure out which things work and which things don't work. So let's start doing this now. Let's get out there and let's build the next generation of event-driven, elastic, secure, durable, available, serverless applications. Let's never pick an AMI again. Let's never pick an instance type again. Let's do things the right way. Thanks, everybody.